Good morning, students. In the last class, we discussed about the atomic mass. So today we start with the composition of nucleus. Right. So in the last class, we considered one example, that is hydrogen. So hydrogen element consists of three different types of masses. Right. So that one we call as proton, deuterium, and tritium. So in the proton, that is in hydrogen, we have only one proton, right? So in deuterium we have one proton, along with this proton one neutral object, that is neutral particle is present. So that one we call that one as the neutron, right? So this is in deuterium. And in tritium, along with this proton, one proton, along with this one neutron, and here one neutron is present, right? So that means nucleus consists of proton, along with this proton we have neutrons also, right? So that may be in any number of protons or any number of neutrons. For considering here example, that is hydrogen. In hydrogen, we have three different types of masses. So one is which consists of only the proton, and in the second deuterium it consists one proton and one neutron, and in tritium we have one proton and two neutrons, right? So here that means the nucleus consists of both protons and neutrons. That is the composition of the nucleus, right? So next, if we write the composition of the nucleus by using these terms. So in the first, that is Z. So Z is the atomic number, right? Where Z is the atomic number, that means number of protons, right? Where Z is the atomic number, so Z represents what? Number of the protons, right? So similarly, next N, right? So N is the neutron number, that means number of neutrons present in the nucleus, right? So on the last one is A, that is mass number, right? Where A is the mass number of the element. That means this mass number consists of both protons plus neutrons. So that one we call as the mass number. So that one is represented by A. Where Z is the atomic number, that means the number of protons which are present in that nucleus is given by the symbol, that one is the Z. So that one is the atomic number, right? So where N is the neutron number of the neutrons which is present in the nucleus. Where A is the mass number, so mass number A is equals to sum of the protons and sum of the neutrons. So right, so for that A can be written as A is equals to Z plus N, right? So when A is the mass number and that is equals to sum of the protons plus sum of the neutrons. So sometimes this mass number is also called as nucleons, right? So mass number is also called as the nucleons because it consists of both protons and neutrons. So that's why these are called as the nucleons, right? So by using this, if we write the composition of the nucleus, then that can be represented by the symbol X here in the A, and it is Z, right? So the composition of the nucleus is symbolically represented as X, A, Z, right? So where X is the chemical symbol, where X is the chemical symbol of the species. So either it may be hydrogen, helium, oxygen, nitrogen. So these are represented by the term X, right? So the composition of the nucleus can be explained by symbolically is AXZ, where A is the mass number and Z is the atomic number, where X is the chemical symbol of the species, right? So if we take one example for this, right? So 197 AU 79, right? So here when AU is the gold, so this one is the gold nucleus, right? So if we write the representation here like this, AU is the nucleus of the gold and 197 is the mass number, that is A. So when A is the 197, that means this 197 consists of both protons and neutrons, right? So if I write where A is equals to 197, that means gold nucleus consists of the mass number, that is 197 number of total protons and neutrons are present in the gold nucleus, right? So next 79. So the Z represents what? Atomic number, right? So Z is how much? That is Z is equals to 79. That means the number of protons which are present in the gold nucleus is how many number? That is 79 number of the protons which are present in the gold nucleus, right? So now we need to find N. That means number of neutrons which are present in the gold nucleus. So by this A is equals to Z plus N. So we can write N is equals to, so here we can write N, that is equals to A minus Z. That is from the mass number. A is equals to Z plus N, right? So we need N. That means keeping N in the RHS, then if we shift Z to the LHS means plus Z becomes minus Z. That means A minus Z gives the neutron number, right? So here if we find the neutron number, then A minus Z, right? So that means here if we subtract 197 minus 79, so here we get 17 minus 9 is 8. Next here 8 minus 7, that is 1, and 118. So this indicates that A is the mass number, that means it consists of 79 number of protons and 118 number of the neutrons. So if we add these two, we get the mass number, that is A. That means total number of the protons and neutrons which are present in the gold nucleus, right? So this is one example, right? So this is the composition of the nucleus, right? So next, in the last class we discussed about the hydrogen nucleus, that it consists of, hydrogen element consists of 3 different types of masses, right? So in that, each having the same proton number but different neutron number. So that can be written as, those isotopes can be written as right. So for hydrogen isotopes, right? For hydrogen isotopes 1H1. That means hydrogen consists of 1 proton and 1 that is 0 neutron. That one is the proton, right? So hydrogen nucleus consists of only the proton, right? So this one is the first, and next is 1H2 deuterium, and the third one is 1H3, right? So this indicates here it consists of 1 proton, 0 neutron, right? So mass number A and Z number is 1. So N is A minus Z, that is 1 minus 1, we get 0, right? So in this deuterium we have one proton. So directly here we are getting Z is equals to 1. That means number of protons which are present in the deuterium is how much? 1. So here we have mass number 2. So 2 minus 1 is how much? 1. So here we get 1 neutron. Right? 1 proton and 1 neutron. So in the third example we have 1 proton. Right? So 3 minus 1 is how much? 2 neutrons. Right? So this is the example. One is gold and second one is the hydrogen isotope. So for hydrogen isotopes we can write like this 1H1. If they ask for deuterium we need to write 1H2. Right? So for tritium we need to write 1H3. Right? So here few more definitions as well. So one is isotope. So in the isotope we can define like this means same Z, that is same atomic number but different mass number of the same element, then that one we call as the isotope. So if we define the isotope means having the element. So here if we observe all the elements are which one here? Hydrogen, right? So here is hydrogen, and here is also hydrogen. In the same element, we have same proton number. That means same atomic number but different mass number. So that one we call as the isotope, right? So similarly, if nucleates having same mass number, right? So here nucleates of different elements. So here if I consider one nucleus that is of hydrogen and if I consider another nucleus as gold, then these two nucleus has the same mass number, then that one we call as isobars. Right? So what are isobars means? The nucleates having the same mass number. That means A value is same for two different nuclei. Then those nucleus we call as the isobars. Right? So for this, if we write the example, that is 1H3 and 2He3. Right? So here if you observe A value is 3 here and here also A value is 3. So here we have the nucleus of hydrogen and here we have the nucleus of helium. Two different elements of two different nuclei having the same mass number. That means same A value. Right? So 3 represents what? A. A is equals to 3. In these two elements having the same mass number, then these two nucleides we call as the isobars. Right? So understand this one. So here two different nuclei are important. Right? Next, the similar we have one more. If nucleides having same neutron number, right? So that means n value is same for two different nucleus, right? So that one we call as isotones. So what are isotones means? Nucleides having the same neutron number. That means n value is same for two different nuclei. Then those two are called as the isotones, right? So here, if I take the example that is 197 AU 79 and 196 AU 80. right? So considering these two nucleus, one is gold and another one is mercury, right? So here the mass number is 197 and here mass number is 198 and here the proton number is 79, here the proton number is 80. So if we find the neutron number here, n, that is equals to A minus Z, A minus Z, 197 minus 79. So here we get 118, right? So if you observe here, the neutron number n is equals to 8118, right? So in these two cases, we have the n value is same, that is 118 and 118. So then these two nucleus we call as the isotones, right? So in the composition we have three definitions. So one is isotopes and another one is isobars and the third one is isotones. So this one is very important. So they ask for the 2 marks definition along with the example, or in 1 marks possibility of asking the definition. So what are isotopes, what are isobars and what are isotones, right? So here the difference between isotopes and isobars and isotones is here having the same element, right? So in isotope, same element having different neutron number, that is same element having the same proton number or atomic number, then those are called the isotopes. But here we having the different elements having the same mass number and here having different elements having the same neutron numbers, right? So in the AXZ, if we have the same A value, then that one we call as isobars. If we have the same Z values, then we call that one as the isotopes. And if the difference A minus Z is same, so that one is the isotones, right? So here we have the three values and here we have three definitions, right? So this is about the mass of the nucleus. So nucleus consists of the protons along with the neutrons, right? So important in this topic is isotopes, isobars and isotones. So here we have one example for this: isobars, isotones and isotopes, right? So this is about the composition of the nucleus, right? So in the next, so this is the first property, that is mass, atomic mass and the mass of the nucleus, right? So the next one is size of the nucleus. So size of the nucleus. So in the last chapter only we discussed, that is Rutherford alpha scattering experiment. He determined the size of the nucleus, that is by conducting the experiment. So which one is that? The alpha particle, right? So alpha scattering experiment. So in that he considered one thin sheet, that is gold foil, right? So the alpha particles which are coming from the radioactive source. So this one is the alpha particle, right? So these alpha particles when strikes the gold foil, then scattering takes place in all the directions. So maximum scattering is low angle scattering and only 0.14% of the scattering will take place with an angle greater than 1 degree, right? So only one of out of 800. So 8,000. Only one out of 8,000 alpha particle is back scattered, right? So this is the experiment which was conducted by the Rutherford while he proposed the theory, right? So by using this experiment, so Geiger and Martin continued the experiment, right? So when alpha particle is the nucleus of the helium atom, so this alpha particle is positively charged. So he found the reason for why it has to take backward scattering means, so this gold foil consists of the atoms, so these atoms consist of the nucleus, right? So that nucleus is closely packed and it is positively charged, right, in a small volume. So this becomes the nucleus. So as alpha particles strikes the nucleus, that means as it approaches towards the nucleus, as this alpha particle is positively charged, nucleus is also positively charged, then by the Coulomb's electrostatic force, these two gets repel each other, hence it will take backward scattering, right? So this is the explanation which was given by the Rutherford. So this is purely basic of Coulomb's electrostatic force. That means like charges repels each other. So here alpha particle is also positively charged particle and nucleus is also positively charged. For that reason this nucleus is sent backward. That means backward scattering is takes place, right? So while doing this experiment, he found the closest approach of the alpha particle to the nucleus, that is the distance of closest approach. So right, so this one is denoted by R0. So where R0 is the distance of the closest approach, so that value is equals to 1.4 into 10 to the power of minus 14 meter. When this alpha particle having the energy E is equals to 5.5 mega electron volt, right? So that is conducted by the Geiger and Martin. That means the alpha particle moving with the kinetic energy 5.5 mega electron volt, then it approaches the distance of closest approacher is how much? R0 is equals to 1.4 into 10 to the power of minus 14 meter. As this is purely based on the Coulomb's law of electrostatic force, he concluded that this nucleus size is very small than this value, right? So the size of the nucleus is less than the value of R0, because from the electrostatic law, that is Coulomb's electrostatic force, or from the Coulomb's law, he says that the size of the nucleus is very small compared to that of the distance. So this distance is what? The distance of the closest approach, right? So if this energy we applied to the alpha particle is greater than, if this energy is greater than 5.5 mega electron volt, right? So next what he did means he increased the energy of the alpha particle. That means this alpha particle moves faster and with a high energy, that is greater than 5.5 mega electron volt. That time the distance of closest approacher becomes very small, right? So this becomes R0, right? So when the energy greater than 5.5 mega electron volt, the distance of the closest approach R0 becomes very small, hence backward scattering, the possibility of the backward scattering is not taking place, because here there may exist the nuclear force, right? That is because of the nuclear force, the backward scattering is not possible, right? So for that he concluded that the size of the nucleus is very less than R0 value, and the R0 value is how much? That is 1.4 into 10 to the power of minus 14 meter. Right? So Geiger and Madsen further continue the experiment by replacing alpha particle into fast electron. Right? So this was the experiment which was conducted by the Rutherford. Now Geiger and Madsen replaced the same experiment by alpha particle into the fast electron and also the gold foil into different types of elements. Right? So Rutherford only considered this one as the gold foil. Then Geiger and Madsen replaced this gold foil into different elements. So bombarded with the fast electron. Right? So from this he found the radius of the nuclei of different elements. After conducting this experiment, that is replacing the alpha particle by the fast electron and also replacing the gold foil with the different elements, and he found the radius of the nuclei of all the different elements. So that value is almost equals to R is equals to R naught into a to the power of 1 by 3. Right? So where R is the radius of the nuclei and R naught is the constant, where A is the mass number. Right? Where A is mass number and R naught value is 1.2 into 10 to the power of minus 15 meter. So where R naught is a constant, so that value is 1.2 into 10 to the power of minus 15 meter. Right? So this gives the size of the nucleus. Right? By using the Rutherford experiment. So this Rutherford experiment already we discussed in the last chapter. Right? So that is in the atoms. So according to Rutherford, he considered one thin gold foil, and this gold foil is bombarded with the alpha particle. Right? So backward scattering takes place. So this backward scattering is due to because of the atoms which consist of the nucleus which are closely bonded together. So as the nucleus is positively charged and alpha particle is also positively charged, hence from the Coulomb's law the repulsive force exerts. So that this nucleus exerts a repulsive force on the alpha particle. Then we have the distance of closest approach R naught is 1.4 into 10 to the power of minus 14 meter, when the alpha particle is moving with the energy is 5.5 mega electron volt. Right? So if you further increase the energy of the alpha particle, then the distance of the closest approach becomes very small. Then the nuclear force, due to the nuclear force, the backward scattering is not possible. Right? So for that he considered this energy is sufficient. And also he concluded that the size of the nucleus is small than that of the distance of closest approach. That is, the size of the nucleus is less than 1.4 into 10 to the power of minus 14 meter. Later, for different elements, Geiger and Madsen continued the experiment by replacing the alpha particle into the fast electron. That means the electron which is moving with higher velocity. Right? So and also he replaced the gold foil with different elements, and he found the nucleus of the different elements. Then he get the radius of the nucleus is equals to R is equals to R naught a to the power of 1 by 3. Right? So where A is the mass number and R naught is equals to the value 1.2 into 10 to the power of minus 50 meter. Right? So this gives the size of the nucleus, and which was given by Geiger and Madsen. Right? Next, as the volume of the nucleus is directly proportional to R cube. Right? So volume, the nucleus is in spherical shape, then the volume of the sphere is 4 by 3 pi R cube. So 4 by 3 pi is a constant value, then we can write 4 V is proportional to R cube. So radius of the nucleus is directly depends on the mass number. That means the nucleus consists of both protons and neutrons. So that one we call as the mass number. So that is directly proportional to A. Right? So from this relation, he given the equation. So by using R cube is directly proportional to A, then he write R is proportional to A to the power of 1 by 3. That means cube root on both sides. So here 3 by 3 get cancelled. So here we get 1 by 3. That means R is proportional to A to the power of 1 by 3. Right? So that is given by, if we remove the proportionality, then R is equals to R naught A to the power of 1 by 3. Right? By using the relation, volume of the nucleus is proportional to cube of the radius of the sphere. Right? So that one is equals to the mass number. Right? So by this we get the relation R is equals to R naught A to the power of 1 by 3. Right? So the density is independent of the mass number. Right? So the density of the nucleus is independent of the mass number, and the density of the nucleus we get so this gives the size, and here if you write density of nucleus, so that value we have 2.3 into 10 to the power of 17 kg per meter cube. Right? Density of the nucleus we get while conducting the experiment, we get the value is 2.3 into 10 to the power of 17 kg per meter cube. So we know the density of the water, right? So the density of the water is how much? 10 to the power of 3 kg per meter cube. That means 1000 kg per meter cube. That is the density of the water. So here if you observe the 17, 10 to the power of 17, and here we have the 10 to the power of 3. That means the density of the nucleus is very greater than the density of the volume. Right? So if you observe here 10 to the power of 17, nothing but 1 followed by 17 zeros. So here that value is greater than 1000. So that means the density of the nucleus is very greater value. So we know the relation density is equals to mass by volume, right? So that means volume is inversely proportional to that of the density. So here the density of the nucleus is very high, right? So if the density of the nucleus is very high, that means the volume of the nucleus is very small, right? So for that reason only the nucleus is highly concentrated and its density is very more, hence almost the atom is empty in space. So this is the reason, right? So here we get the size and here we get the density. So from the density of the nucleus we conclude that volume of the nucleus is very small. Because it is densely concentrated, for that reason all atom is almost empty, right? So this is the conclusion which is given by using the density, right? So the density value is 2.3 into 10 to the power of 17 kg per meter cube. So this value is very greater than that of the density of the water. That means density is very large. So if density is more, then automatically the volume is very small, right? So as the volume of the nucleus is very small, hence the atom is almost empty right? So this is also explained by the Rutherford also, right? So this is about the size of the nucleus. So size of the nucleus, R is equals to R naught a to the power of 1 by 3, where R is the radius of the nucleus, R naught is a constant and that value is 1.2 into 10 to the power of minus 15 meter, and where A is the mass number, right? So this is about the size of the nucleus. So next topic. So next one is mass energy and binding energy, right? So as already we know different forms of energy, that is kinetic energy, potential energy, light energy, electrical energy. So these are all the forms of energy. So Einstein given that mass is also a form of energy. So here in this chapter, so Einstein gives that mass is also one of the form of energy. We can convert mass energy into the another forms of energy. That means we can convert mass energy into electrical energy, that is kinetic energy, and we can convert that one kinetic energy from kinetic energy into mass energy, right? So Einstein proposed that mass is also the form of energy, and he gives the relation, that is E is equals to mc square, right? So that one is we call as energy mass relation, right? So Einstein says that mass is also one of the forms of energy. We can convert mass energy into, we can convert mass energy into other forms of energy, right? So that means we can convert mass energy into kinetic energy, and we can convert kinetic energy into mass energy, right? So that's the relation is with E is equals to mc square, where c is the speed of light in vacuum, speed of light in vacuum, and this value is 3 into 10 to the power of 8 meter per second, right? So this is the mass energy relation. Einstein's energy equation is E is equals to mc square, where m is the mass, c is the speed of light in vacuum, and that value is 3 into 10 to the power of 8 meter per second, right? So energy equivalent of, for example, if we consider one example, that is energy equivalent of 1 gram substance, right? So here mass of the substance they given is how much? 1 gram, right? So if we find the energy, then we know E is equals to mc square. We can convert, that is mass, in the form of energy, right? So 1 gram is how much? That is 10 to the power of minus 3 kg, into the speed of light is how much? 3 into 10 to the power of 8 whole square, that is meter per second, right? So here we get 3 square, that is 9 into 10 to the power of 8 square, that means 16. 8 plus 8, 16. 16 minus 3 we get 10 to the power of 30. So energy is joule, kg meter per second. So that one, this is about the mass energy. So in the next class we will continue with the binding energy. Right? Thank you.